Okay, today we are going to talk about the condition for degeneracy in stars, and also we will talk about degeneracy pressure, which plays a very important role in the stellar evolution. Okay, but before that, let me talk about this degeneracy first. So, what is degeneracy? Well, you see, degeneracy is basically a quantum mechanical effect which modifies the equation of state. Okay, now you know, in classical physics the states of free particles, they have, right? Yes, they have a continuous energy spectrum, and also there is no limit on the number of particles that can be found in these continuous states. We do know that, of course. However, under certain conditions which are sometimes found in stars, quantum physics can also play a very important role for the free electron gas. And what happens is that when quantum physics start becoming important, they start playing a role, then the free electron gas, I am right now talking about the electron gas only, then we say that the gas becomes degenerate. Now, degeneracy for such a gas, you see, is due to a combination of the Heisenberg's uncertainty principle and also Pauli's exclusion principle. Okay, so the main reason for degeneracy is the result of combination of Heisenberg's uncertainty principle and Pauli's exclusion principle. Now I am going to talk about it in more details. Now, you see, what happens if the wave functions of gas particles in a gas, they begin to overlap? What happens? Well, then we will need to take into account quantum effects, and two very important quantum effects are uncertainty principle and exclusion principle. But note that this thing, which means the wave function of the gas particle beginning to overlap, when will this happen? This will happen only if the density of gas is sufficiently high, and also the temperature is not very high. So high density but little bit low temperature, but these are figurative right now. Now, if the temperature does not increase enough, then what happens is that a significant fraction of the lowest energy states can be filled up, and the collisional energy, the energy due to collision among the particles, right? The collisional energy, they cannot elevate the low energy state particles up to the energy of the unfilled states. And then we will consider the case for the effect of quantum mechanics for this gas. Now, let me talk about this a little bit more details. Now, suppose in a volume V, there are capital N particles. Okay, then what will be the volume of one particle? So volume of one particle, it is V by N, right? Now, if lambda is is the distance between two particles. Then what can we say? Well, you see, we can say that this thing, right? This is the dimension, you can say. And from here we get a value of lambda s, which is equal to 1 by n by v to the power 1/3, or this means 1 by number density to the power 1/3. Right. Now, so we have got a relationship, a very basic one, for the distance between two particles in a gas in terms of the number density. Okay. Now, what about the de Broglie wavelength? Well, the de Broglie wavelength, we know that this is given by h by p, right? Now, as you see, we have half mv square is equal to half kVt, and so from here we will get mv is equal to root over m kVt. Fine. So this means that so this means that we will get lambda b, the de Broglie wavelength, h by p, it will become h by root over m kVt. Fine. So this is the relation for the de Broglie wavelength. Now, as I was talking just now, I was talking about the comparison between the de Broglie wavelength. Remember, I was talking about the overlap between the two particles. So basically I am comparing the de Broglie wavelength and the distance between the particles. Okay. So what happens under this case? What is this? You see? Yes. So this is the first case. The de Broglie wavelength is smaller. So this is case 1. So what happens when the de Broglie wavelength is smaller than the distance between the particles? Well, then from the previous two expressions, this one and this one, on comparison we can immediately say that this means that h by kb is the Boltzmann constant, is less than 1 by n to the power 1 by 3. And when is this possible, this thing? Of course, as you can see from the expression, this is possible for large temperature and also for small number density. And this is basically the regime of Maxwell-Boltzmann statistics. Okay, and when this thing happens, what we can say is that the first thing we can say is that the particles are non-interacting. So basically you are dealing with classical particles. And also we can say non-interacting means there is no mutual interaction between the particles. And also the second thing which we can say is that the particles are individually distinguishable. Okay, so these are the two things we can say when the de Broglie wavelength is less than the distance between the particles. What about the other case, which means when the de Broglie wavelength is greater than the distance between the particles? Okay, now so you can just see the very expression and you can immediately arrive that this thing will happen for small temperature and large or very large, basically very large number density, right? And in this case we will have either Fermi Dirac statistics or Bose-Einstein statistics. But since we'll be talking about electrons and later on neutrons, so basically we'll be interested in the effect for the Fermi Dirac statistics. Okay, now when this thing happens, then for fermions, and again for fermions, what we can say basically is that the particles are indistinguishable. Sometimes also the particles are degenerate. Okay, no, you see, along with saying that there is a mutual interaction between the particles, we can say this thing. So what we can say, mutual interaction between particles, this is the first thing we can say. Also we can say that the particles are indistinguishable. Now this is both true for the Bose-Einstein as well, statistics as well, and also the particles are degenerate. Now when I say particles are degenerate, this means this condition, because of this condition, which means their wave functions now start becoming overlapping with each other. Okay, now you must be thinking that well, you are talking about degeneracy in stars, right? What about Earth? What about this smartphone I am having, right? What about the electrons in the metals which have made this smartphone? Well, you should be amazed to know that, you see, the free conduction electrons inside metals, they are actually highly degenerate since the number density is very large. And in fact, most metals are very hard to compress, and this is a direct consequence of the high degeneracy pressure of the conduction electrons. Okay. Now here I have discussed about the condition for degeneracy to be the overlap condition of wave functions. Now this is quite vague idea, but good idea. Now there is another way in which we can talk about the degree of degeneracy. When comparing say two or more stars, if someone asks that whether the degeneracy is more in this star or in this star, how do you do that? Now there is another way to do this, and we will talk about it right now. Now the first thing I would like to say that I'll be considering here only the electrons. Okay, so I'll be talking about only electrons, and the reason is because their behavior is very important during the evolution of stars. Now nucleons also become important, but at the very end of the evolution of the massive stars. And once we do the formalism for the electrons, then the formalism for the nucleons is quite straightforward in that case. Now let us begin by determining the energy levels of electron confined to a region of space defined by the volume of the star. Okay, so first let us consider a cubic box of volume L cube. Then the wave function for free particles which are confined to the box. What are the wave functions? Well, we can write it as quite straightforward. Yes, so these are the wave functions. A very simple one. Now this is equation 1, and well, as a result of this, the momentum you can write as P is equal to h by lambda. Now we are right now considering non-relativistic case, NR case. Then what will happen? So basically we are talking about E is equal to P square by twice M, right? And so we will have this relation. Okay, so this is because of this similar, and this is equation 2. Now this n square, note that n square is basically equal to nx square plus ny square plus nz square. Okay, now fundamentally this is the result of the uncertainty principle, this one. In that, the minimum momentum of a particle is constrained by the maximum volume that the particle may occupy. Now from the exclusion principle, we know that no two fermions can occupy exactly the same state. If the temperature is 0 Kelvin, then all the states up to some maximum value of capital N, right, will be filled with electrons. And since there are two spin states allowed for each energy state, and the total number of electrons in the gas is any, you see, again let me write it down. So note that since there are two spin states allowed for each energy state, Nx, Ny, Nz, the total number of electron in gas any that are in ground state of, you see, the entire population of electrons in star, they correspond to twice the total number of unique quantum numbers Nx, Ny and Nz. Now since there are a very large number of electrons in a typical stellar core, the discreteness of the states washes out, and the number of unique quantum numbers corresponds to the volume of 1/8 of a sphere of radius n is equal to this thing. So we can write here. Okay, now this is equation number 3. So this is the expression for Na. Now if we solve for n, then we will get this result. This is equation number 4. So solving, we get this. Now, so what do we get? So we observe that at t is equal to 0, t T is equal to 0, all electron states with energies below a certain energy will be filled with electrons, and this energy is known as Fermi energy. Okay, and how do we get this? Well, this is quite simple. For that, we substitute equation 4 in equation 2, and on doing that you will see we will get the Fermi energy, and it is given by this here, equation 5. So this is the Fermi energy. Okay, you see the EF for Fermi energy, and here Ne is equal to basically capital Ne divided by L cube. Right, so basically it is the number density of electrons. Now you see, since all the states below this energy are filled, then the number of electrons with energy between, yes, let me write it. So since what I was talking about, so since all the states below this energy EF are filled, so the number of electrons with energies between E and E plus dE is equal to twice, you see, twice the number of states in this range. And so we can write like this. You see, this is the 2 factor over here. So this is equation 6, and here we have used basically this expression for N, which is equation 7. Now note that this condition, okay, this condition holds when the temperature of the gas is 0 Kelvin. But if the temperature is above 0 Kelvin, then what happens? Then some electrons will have energies above the Fermi energy. Now we take a look at this picture I am showing you here. This picture here. So basically here the number of occupied states is shown as a function of the energy, right? Now this vertical line here, this vertical line indicates the number of filled states at t is equal to 0, right? And the shaded area, this one, what are these? This basically indicates the number of electrons that can contribute to the thermal energy of the gas, okay, at finite temperatures. Now you see the amount of extra energy is about 3/2 kBT. Let me write this down. So the amount of extra energy is about 3/2 kBT. Therefore, electrons with energies above EF minus 3/2 kBT can move to high energy states, right? They can move to higher energy states through collisions. and those with energy less than this amount. Here, energies less than this amount, what will happen to them? They have in fact no empty space to move up to, right? Now we can relate the condition for degeneracy to a limit on the temperature and electron number density of the gas. Now in particular, it is important to note that the gas is completely non-degenerate. So gas is completely non-degenerate if by 2 kBT is less than equal to 0, because you see all the electrons can exchange energy and therefore contribute to the ideal gas equation of state. Thus the condition for degeneracy is basically Fermi energy greater than equal to 3 by 2 kBT. Now, in order to relate this condition to the primary quantities, what are our primary quantities? Remember these three. We note that the number of electrons per unit volume can be calculated, you see, and the value is given by this one here. Now this is equation 8, right? Now, so from here and our previous discussion, we can get a value of Fermi energy. So let me write down the entire expression for you. Yes, so this is the expression for Fermi energy, equation 9. Now if we set, now let us set 3 by 2 kBT is less than equal to EF for degeneracy. Then you will see we will have this relationship. Okay, and again if you work this out furthermore, then you get basically this relation here. Now this is very important. So this is equation 10 and this is equation 11. Now for here you see average value of Z by is also here. Now we note that for typical elements above hydrogen, what is the value? This value is approximately 0.5, right? So if we put this then and put the other values H cross square, Me and Kb Boltzmann, if we put all of these values, then you see we will get that this condition becomes like this. So this is the condition for degeneracy. Okay, note that the smaller we have this quantity, the more degenerate the gas. So this is important. So what we do is, so if I ask you to compare 3 stars and ask you which one is more degenerate, then what you have to do is simply calculate for each of them this quantity, T by rho to the power 2 by 3. And remember, this is the condition for degeneracy, right? And the lowest one will be the star which has the lowest value of T by rho to the power 2 by 3 will be the star which is the most degenerate among the three of them. Okay. So we have discussed about degeneracy in terms of the overlap of wave function, right? We estimated the value of de Broglie wavelength and compared it with the interatomic distance. There was a discussion on that. Later on, we arrived at a more you can say descriptive discussion on how to consider how the degeneracy, the degree of degeneracy of a gas. So we arrived at this condition here, right? So what is the equation number? So 7, then 11. Okay, so this is 12 basically. Yes, equation 12. Now what I am going to do, I am going to write down or basically derive very simply the equation of state for a degenerate gas. Now you